I think you're on mute. I can't see if you're talking.
You are definitely on mute.
Yeah, can you see my slides?
We can.
Okay, all right. Sorry, okay. I'm trying to get rid of this. All right. So, so this theme is at the intersection. So it's a pretty broad theme where there's really some concrete projects around sampling and concrete projects around optimization. And I need to actually tell you about the connections between them. So I was a little torn between, you know, introductory talk or really going to an overview of various questions. I decided to stay to present a fairly introductory talk on that, what I think is probably one of the most fascinating aspects of the interface between sampling and optimization. All right, so just to present the team that's working on this. So it's a team, 4 people at MIT, 4 people at Berkeley, and Francesco Rabona at Boston. So the objective of this team is to, so the one-line summary is to develop a... I'm sorry?
If you're advancing the slides, it's not showing up for us.
Oh, I see. Let's see. Maybe this. Bring your shared window to the front. Oh, I know what I need to do. Okay. Sorry about that. Let me share. No, I don't think I know how to do this. All right, let me. That's probably the safest one. Okay, so can you see the slides now? Okay, good. All right, so the team has, as I said, four researchers from MIT, from Berkeley, and Francesco from Boston. So the objective of this theme is to develop a combined perspective that allows us to make progress both on optimization and sampling. And there's some really two-way connections between the two. There's also some interesting connections to PDEs, which I will not mention in this talk. And actually, I will mostly mention how to use optimization techniques to advance our understanding of sampling. All right, so what is sampling? Well, sampling is actually becoming something which is pretty topical, especially thanks to websites such as This Person Does Not Exist. And you go there and you have like some beautiful pictures that are generated by GANs or variational autoencoders, and you press and you keep on getting some very realistic photos. Some look less realistic than others. And then what you get is a way to generate new data. But of course, this is not a new question, right? So of course, sampling is a central question in Bayesian statistics, actually, perhaps the most central. When you think about MCMC, there's a huge amount of research interested in sampling, especially from high-dimensional distributions, and it arises in a variety of applications. One is online algorithms that was mentioned by Mike, where you're trying to explore and you need to sample your space in an efficient manner to explore this. So I'm going to look at a very stylized problem around sampling. I'm certainly not going to be sampling faces. I'm going to sample from a density. And the standard setup in Bayesian statistics is that you know your density up to normalizing constant. This is your posterior, the product of your prior and your likelihood, and you don't know typically what the normalizing constant. And here we'll focus on the log concave density, where I can always write pi as e to the minus v for some convex v, okay? And a standard tool to sample from this, a central tool, is this Langevin diffusion. And the Langevin diffusion is a stochastic differential equation, which is given in this frame here. And it's just dxt minus grad v. So you have a drift term, which is given by the negative gradient of v. So it's pushing your particles towards the minimum of v. And then you have a stochastic term, square root 2 d Brownian motion at t. So this is just something that gives you, if you didn't have this part, you would just go to the minimum of v, and you want to actually have a sample with some entropy in there. And it's well known, this is a standard probabilistic result, that this has the right stationary distribution, which has density pi. Of course, in practice, we don't implement this continuous time stochastic differential equation, what we do is we discretize, and a lot of work goes into understanding what level of discretization we should be using. So this formula down there is telling you that here you have a step size h, and finding the right h is still very much an active area of research, which I will gloss on throughout this talk. Okay, so what is the connection with sampling and optimization? Well, if you look at the stochastic differential equation, you look just at the first part, so you forget the Brown motion. As I said, this is just a gradient flow, and it's trying to minimize this V. So clearly there is an optimization in gradient here, okay? This is a basic gradient flow. And of course, you add a stochastic term, but who is afraid of stochastic optimization nowadays? Stochastic gradient descent is a very popular algorithm. And so this is a very standard connection between sampling and optimization. And in fact, this perspective is what has driven Dallaglione in 2014 to essentially revive the understanding of Langevin algorithms, and by saying, well, we have a lot of well-developed techniques to analyze gradient descent or stochastic gradient descent. I can open lecture notes from Nesterov or from Bubek and just apply those techniques, and that's very much what he did. And the conditions were weakened later on by Durmus and Moulin. Okay, so a fruitful perspective, but almost a very obvious connection between optimization and sampling here. So the geometric picture I want you to see here, and geometric is the first name of this theme, is this. Okay, so here we want to think of our particle xt as moving as a trajectory on Rd. Okay, so we have this space of particles, xt lives on Rd, and it follows this, sort of a Brownian, gradient flow with some stochastic drift. So it kind of looks like a Brown motion, but it's going down. Okay, so you're on a flat space and you have something that's moving around. But in fact, I argue that what I would like to emphasize today is this second take on optimization, where we're not thinking about what the geometry of the trajectory of xt is, but the geometry of the law of xt is. All right, so xt has some probability distribution that evolves over time, and you're trying to understand how is this thing changing over time. Okay, and so I'm going to put this, and I have a curve of trajectories that starts at mu0, goes to mu infinity. We know that mu infinity is the one that has the right density pi, and we'd like to understand this curve. And if we can understand this curve, how fast it converges, then we can actually understand the rate of convergence of the Langevin diffusion, for example. Okay, but to understand this, I need to understand what space am I even showing here. So there's this curved space. It's a space of probability distribution. It will be curved, so there's many spaces of probability distributions we can think of. But we want to think about the right one for this problem. And this right one will be the Wasserstein space of probability distribution, which is a space that arises using tools from optimal transport. So let's open a brief parenthesis on optimal transport. And probably by now, everybody's seen optimal transport, but let me remind you what it is. So the idea of optimal transport is that you have a pile of dirt. So when Monge introduced it, he talked about déblai, which is a pile of dirt, and you're trying to fill a ditch somewhere, and it's called a remblai. And he was trying to minimize the amount of work, the amount of distance that the dirt had to travel to fill those gaps. Okay, so what he's trying to do is to try to find what's called a transport map, which is a valid way of moving the dirt from one pile to the ditch. And also, among all possible ways to do this, he was trying to find the one that would minimize the amount of work. Okay, so those maps, those valid transport maps. So we're going to think of the pile of dirt mu as the pile of dirt, the déblai, as being a probability distribution, so volume 1, and the remblai, of course, it has to fit the dirt, so it's going to also have volume 1, and we'll call it nu. So you have two probability distributions. And having a valid transport map, something that really takes the pile and put it in a ditch, is so-called a transport map. In probabilistic terms, we say that T pushes mu to nu, and this little hashtag notation is doing just that. Okay, so this is just saying that if X has distribution mu, then T of X has distribution nu. And so many ways to do this. And what Monge advocated was to take the one that minimizes the expected amount of work that you need to travel. Okay, so what is this amount of work? Well, you look at the distance between X and where it goes, T of X. Okay, so you take the difference between those two, take the squared norm, and then this is a random quantity. You average it over all possible starting point X distributed according to mu. So that's the distance, the average square distance traveled by a grain of sand, say, coming from the pile of dirt mu. And now, among all possible ways to travel, you're trying to find the one that minimizes overall valid ones. Okay. So it turns out that this this quantity here, so it's homogeneous to a square, it turns out that this thing is actually a square distance. Okay, so this is a square distance. It's the minimum here exists and is unique if mu has a density, which will be the case because we're talking about a diffusion. So as soon as time is strictly positive, you are completely diffuse. And so for the example of the Langevin diffusion, all mu t's for positive t are diffuse. And now I have this thing which defines the square Wasserstein distance, W2 squared, between mu and nu. Okay, so it's not trivial that this is a square distance, but it is. And so it's in fact the 2 Wasserstein distance because of this power 2 over there. And you could take a power p and that would give you the Wasserstein p, but here for this talk, we only care about Wasserstein 2. And it gives you a distance, not over all probability distributions, like let's say the total variation would. It's giving you only on those for which there is a finite second moment. Okay, you need to be able to talk about the expectation of the square, but that's essentially the limitation here. Okay, so I just mentioned another distance, total variation, and you probably know other ones. There's many distances. If you have a density, you could talk about the L2 distance or L1 distance between your densities. There's many ways to think about distance between probability distribution. This one seems complicated, and the question is, why would you do this? So let's just look at the geometry that it induces. Okay, so here I look. So the way you think about a geometry between probability distributions by looking at midpoints. Okay, so if I take mu and nu, okay, so I have to the left I have mu and to the right I have nu, and I'm interested in what is the average in L2. So that would be the average of the 2 densities. So that's a mixture, the density of the mixture between those 2 distributions. Well, it's really just 1/2 of the first function plus 1/2 of the second function. So you see those 2 bumps, one corresponding to each of them with weight 1/2 each. And what Wasserstein does, so of course you can vary the weight. And what Wasserstein does is that it actually essentially puts a midpoint which is slowly moving the mass from where the mass of mu is to the mass of nu is, but on the x-axis rather than on the y-axis. Okay, and this curve that I'm showing you is a geodesic. All right, so that's basically the space of convex combinations between mu and nu in that sense, and that defines an average in Wasserstein space. So what is this geodesic? Well, there's actually a very simple form for it. So this geodesic is a point, so it's going to be a space is the equivalent of straight lines in this curved space, a shortest path, and it's essentially, so it's going to be a distribution, and a distribution that's at time t on this, say, unit speed geodesic that goes from time 0 to 1. At time 0 is at a mu, and at time 1 is at nu, is the distribution of this convex combination of x and its transported version, where t here is the optimal transport map that arises from the definition of Wasserstein. All right, so if you look at the first line, I say that Wasserstein squared is the expectation of this specific transport map. So that's the argument. And now what I do is that I sample x, I look at where it goes, t of x, and I take the convex combination between the two, and that gives me the distribution along the geodesic. Okay, so we understand very well those geodesics. So now we have a space, it's a geodesic space. We have a space where not only is it a metric space where we have a distance, but we can also define geodesics between those points, okay? So we start having more and more structure on the space of probability distributions. What we're missing now is a differential structure. I would like to be able to take derivatives. And this thing is infinite dimensional. It's actually not homogeneous at all. So I would like to say somehow that it's a Riemannian manifold, but it really is not, okay? It's missing a lot of the properties you would like from Riemannian manifold. But it turns out that there's something that was invented by Felix Otto now called autocalculus, which is a way to define, and at first it was done formally, and later on it was made completely rigorous by mostly by the work of Ambrosio, Gili, and Savary in their book, where on gradient flows, where you can define notions of gradients and define an entire differential structure, which essentially allows you to manipulate the Wasserstein space of probability distributions equipped with the Wasserstein distance as if it was a Riemannian manifold. And so, of course, the thing for having a differential structure, you need to know what velocity vectors are. Okay, so I have this curve. It goes from mu to nu at unit speed. That's what it is. And if I'm able to define a tangent vector that tells me what the velocity at initial point is, then I'm golden. I actually can define it everywhere. And here, the velocity is precisely given by the transport map between mu and nu minus the identity. That's what my velocity is. And that's what's going to play the role of velocities. And that's why I need to have densities, because then otherwise the transport map does not exist. And actually, most of the work in defining this differential structure is to extend it beyond the case where you don't have, when you're at points where there's no density. So now that I have this differential structure, I can start talking about derivatives and gradient descent and gradient flows. So this book, sometimes called the Bible, by Ambrosio G. Savare, is telling you everything you want to know about gradient flows on metric spaces, actually geodesic spaces, and more precisely this Wasserstein space. And what it does is say, okay, let me give you a functional on the space of probability measures. Okay, so you give me a probability measures, I'm going to spit a real number, f of mu. And here I gave you 3 examples of such measures. There's this linear form, integral v d mu. There's the KL divergence between mu and nu, or the chi-square divergence. You can think of many of them. And for those, I would like to be able to define what is the gradient of this functional. So meaning I would like to know how this functional behaves when I perturb mu a little bit on this Wasserstein space. And this notion of gradient is, of course, very much tied to the distance that I equip the space of mu's with. And you have explicit forms for what it is for these 3 examples. And there's actually there's an entire calculus which is in place that allows you to compute this. And it's important to be able to do it with several of them. And what it gives you is a way to define a gradient descent. So here I'm using completely non-standard terminology, but I would like to emphasize the fact that I would like to say that I have this curve of probability measures mu t, and I would like to tell you how it evolves. All right, so this mu dot t, you really should think of it as the velocity of mu, of a curve mu t, when I move from t to dt. Okay, so there's a velocity for each curve, and this will just be minus the gradient of a functional. It's of course here the Wasserstein gradient. And if you look at those 3 examples, what is the nature of the Wasserstein gradient? Well, look at the first one. It's grad v dot. Okay, so it's basically a vector field on RD, all right? So grad V at X, for example, just gives me a vector at X. And so that gives me a gradient field, a vector field everywhere, okay? And so the grad of F gives me a vector field. And the way you want to read this is by saying that if I think of a particle xt, which is distributed according to mu t, the way it evolves, so the dot that you see here when you see xt dot is the real one. So that's the derivative of xt in RD. So the way it evolves is by minus this velocity field, grad w of f at mu t, when I apply this at the point xt. Okay, so what I'm really showing is, so that's the way to implement this gradient field, this gradient flow, by thinking at the particle level. But the important part is to think of it as really describing a trajectory on the space of probability measures. So now that I have this gradient flow perspective, I can see what happens if I look at specific functionals. Okay, so here, for example, let's look at the functional which is the KL between mu and nu, and very soon I will take nu to be the distribution that has density pi, as I started from. And so if I plug it in, so I just told you in the previous slide that the gradient of the KL is grad log d mu t over d nu, okay? And now what is d mu t over d nu? Well, log of this. I have the grad log d mu t, I cannot really do much about it, but then the d nu is e to the minus v as a density. So when I take log of this, I get v. And so I'm looking at now grad v. Okay, so I have mu t, which looks like minus grad v, which moves like minus grad v, and then there's this extra term minus grad log d mu. Okay, so now the way you want to think of this, again, this is really at the particle level. So what I'm really doing is that if I have a particle, so look at the last line here. If I'm looking at xt, which follows mu t, then after a little bit of time, say t plus dt or t plus h, I'm moving, I'm close to xt. And the way I've moved is by moving in the direction of grad v and also in the direction of grad log d mu t. Okay. So now this is almost our gradient descent, except that, or stochastic gradient descent, just like we had in the discretization of Langevin, except that in Langevin, we had this Gaussian term that was just like pure Gaussian noise that's slapped onto this. And here we're looking at this weird thing, which is grad log of the density at the current time. And the beauty of this theory is this almost, I'd say, transformative work by Jordan Candelero and Otto in '98, which showed that, in fact, as h goes to 0, this converges to the Langevin diffusion. All right, so you have this deterministic maps, right? Everything here is deterministic. It's saying move xt plus h is xt minus. So here grad v is deterministic, grad log d mu t is deterministic. Everything's moving deterministically. And what it says is that the curve that you will get by doing this deterministic moves that follow this gradient flow of the KL is the same as what you would get if you were to run this Langevin diffusion. So let's pause for a second and try to understand what's happening here. We showed that when I run this Langevin diffusion, I'm going to converge to pi. But what it's really telling me, what this JKO picture is telling me, is that in fact, what I'm doing is this gradient flow. So I'm doing steepest descent on the KL divergence, which of course at the minimum will go down to pi, right? Because I need to have KL which is equal to 0 once minimum. And I'm following this. So in a way, Langevin is basically going as fast as it can towards pi in this sense. Now, one thing I did not mention is that the KL in the Wasserstein sense is actually a convex objective. So it's called geodesically convex. This is the equivalent of convexity on curved spaces. And essentially, you will have all the properties, you know, strong convexity implies exponential convergence. A lot of these things are happening in the same way. But now what's important is that we've moved from this perspective of stochastic differential equations, diffusion processes, all the way to optimization. And now we're representing this idea of sampling as just optimizing a functional over Wasserstein space using here gradient descent. And the natural question is, can we just unleash the arsenal of convex optimization that we have to actually tackle this problem and solve it faster? So one remark here. So now what I've understood is that the curve that I was describing, now I even know at each point what its velocity is, and it's minus the gradient of the KL at mu t. Okay, so that's how I've described what this curve that I was moving in Wasserstein space. This curve space is the Wasserstein space, was the negative gradient. All right, so of course, now that I have this optimization perspective, this enables me to derive not only rates of convergence and use all the machinery that allows me to understand what structural properties do I need on pi so that I get fast convergence, and also can I actually use faster algorithms. So as I said, the objective is convex. So just like convex optimization is very developed. So this is my go-to book on convex optimization. I'm sure everybody has their own. The question is, can we leverage this extensive toolbox to both design and analyze sampling algorithms? Okay, so we've talked about gradient descent from gradient flow, but we could do mirror descent, we could do Newton's method, we could do proximal method, we can do Nesterov's acceleration, and you can think about your favorite optimization algorithm and try to apply it to that case. And for example, so in this year's NeurIPS, we have a paper that explores mirror descent and Newton's method from this perspective. Peter, I mean, there's a bunch of work from Berkeley that explores Nesterov's acceleration. Proximal methods are being explored also as we speak. So all these things is actually a very natural playground for people who have some strength in optimization. So the next thing I would like to do is to try to think beyond diffusions. Okay, so here, everything we've been doing was thinking of a diffusion process, which is what we really implement as an optimization problem. And the two examples that I gave when we're talking about Newton or mirror, we're actually also doing a diffusion and viewing it as an optimization. Can we tackle the optimization directly? Right? There was a deterministic map involved when we were pushing here. So look again at the second line, mu t plus h. So what I'm doing is I'm just pushing mu t by a deterministic map. Okay, so my particle xt is moved to xt plus h using a deterministic map, which is this gradient. Okay, this gradient, this Wasserstein gradient. And so now what we want to do is try to know if we can actually implement this deterministic push forward map. Okay, can we do this? Well, the problem is that if you look at what you can do, so there's the identity, that's certainly fine, h grad v certainly fine, but then there's h grad log d mu t. And that's a problem because you don't know what the distribution at time t of your particle is. You have just this one xt that's moving around. Let's think about what Langevin would do. He would just evolve one vector xt, and then you don't know what its distribution is. You just know essentially what its location is. And so it's unknown, but there's actually a trick that you can apply. Okay, so of course, this is usually when I stuff my complicated slide, so I'm going to go quickly. But there's like a very simple way to think about how to do this. And the way you can do this is by saying, well, I don't know what this grad log d mu t is, but I can hope that if I integrate it against the kernel k of xy, then this thing will actually be close to it, and that I can actually implement. And in fact, you can. All you have to do is to recognize what the form of grad log is, and then apply the integration by part. So where you see the minus sign show up, this is really just the integration by part. And at the end, what do you get? You get something which is just an integral d mu t. And if you want to compute an integral d mu t, then all you need is a bunch of particles, let's say IID particles, mu1 to mu n, so that, x1 to xn, so that when you average them, you have something which is close to an expectation d mu t. And that's what happens in this so-called Stein variational gradient descent. Sorry, I forgot to put the reference. So this is definitely not something we came up with. It's actually a very popular algorithm right now. And in Stein variational gradient descent, what you can do is just evolve a system of interacting particles to actually, in a completely deterministic fashion, so that you actually end up with something that has the right distribution at the end. Okay, so here's the idea. This is what the evolution of each of the particles look like. So the jth particle is moving according to this thing. So it has a bit of a gradient, but then it evolves like this gradient of the kernel is basically making all these particles interact together. So I'm not asking you to understand this, but what we did in this direction is that so there's some observation that this can fail to converge in practice, and there's very little guideline on how to choose the kernel and how to analyze this. So this can be viewed also as, of course, the way I described it was as being the gradient flow of the KL, but you can actually view the same algorithm as being the gradient flow of the chi-square. And in that case, you actually can achieve some strong guarantees, and you can modify the algorithm to get better behavior. So this is a second paper that we have at NeurIPS together with my group. And just to show you how those things behave, what it means to have a deterministic map. So here I'm trying to sample from this bimodal distribution, which is a mixture of two Gaussians in R2. And this is how the particles evolve. All right, so LAWGD is the algorithm that we propose, and it's evolving completely deterministically and settling according to some distribution that looks like this mixture of Gaussians, whereas SVGD is actually moving around quite a bit, okay? And actually, this is one of the things that you can identify from SVGD is the fact that you're kind of keeping some purely rotational component in your velocity field. All right, so to finish, I would like to give a plug. So out of this project was born a Simons Institute program on geometric methods in optimization and sampling. You will notice the edit distance one with the name of this theme. And so this is a program that Peter helped us put together, and it's meant to bring people from the variety of communities that are involved in this kind of project. So optimization, statistics, PDEs, pure mathematics, calculus of variations, etc. It will take place in the fall of 21, and if you want to know more about it, I encourage you to go see the Simons Institute webpage about it. Thank you.
Fantastic. Thanks, Philippe. So we're actually out of time. If there's a quick question, go to the Q&A. Otherwise, you're welcome to go back to GatherTown. The link should be in the chat. Let me post it again if you, oh, it's just, Jesse just posted it again in case you weren't here when that was posted. All right. Thanks very much. Thanks, Mike and Philippe.